Thank you so much for this very nice introduction. It's a great pleasure to be here in Aachen. Right, so I'm going to talk about some joint work with Eduardo Abicaba and Simon Brenners, my former PhD student. Right, so let's go right into it. The subject of my talk will be stochastic Volterra equations of this type here. So you see, these are equations. So here, Brownian motion is driven by Brownian motion as usual. Let's focus on the one-dimensional case. You could generalize this, but let's not do it for this presentation. The most important feature here is there's a memory kernel K. So you see that if you update time, let's say you go from t to t plus delta t, you see that the increment of x does not just depend on the value of x at time t, but it actually depends on the whole history of process x from time 0 through the interactions of this memory. These processes are very, I would say, increasingly more and more popular. And there are many applications in very different fields. Turbulence, I guess, is the most classical application. There's also, this can also be used, for instance, to model self-excitation phenomena. I see, I mean, for instance, let's suppose that instead of Brownian motion, we have a jump process, and the intensity could be modeled by something like this. So the applications in biology, in seismography, but also social sciences, and in economics. So keywords are long and short memory. And I am going to tell you a little bit more about some economics application a bit later. But from a numerical point of view, or also from an analytical point of view, there are some key challenges that these processes pose. In particular, as I already mentioned, this process is not a Markov process. So basically, a whole machinery of methods are somewhat out of the window. I mean, yeah, are somewhat out of the window. There's typically going to be high computational cost. I mean, you see, even if you do a naive discretization of a dynamic like this, every time step would require you to recalculate a whole integral over time. So it's kind of quadratic cost rather than linear cost. Similar, the memory footprint of standard algorithms can be a problem. And in the particular application that I'm thinking of, we also have problems regarding roughness, or if you want stiffness, which come from the choice of kernel, because we are going to look at singular kernels which explode at time 0 on the day. Right. So, as promised, my application that I'm most interested in is coming from finance. And here the idea is you have a stock or an equity model. So ST is the price of a stock or of an index, something like this. And let's say most popular models are of so-called stochastic volatility models. That means that if you think about the increments or the log increments, so we are on a geometric scale here, the log increments of the price, they have a standard deviation which is itself random. So it's kind of locally Gaussian, if you like, but with a random standard deviation, because I mean this comes from data. You see that this actually changes a lot over time. And here it turns out that this standard deviation, not so much the stock process itself, but the stochastic volatility process or stochastic variance process, that there is memory in this process. In fact, so which is why this kind of stochastic Volterra framework is a useful framework for modeling stochastic volatility. So the keyword under which this is known is rough volatility. Indeed, there is actually two ways to look at market data. You can look at time series of market prices. Those are the kind of things that you kind of see visually represented in the news. And here you see, or you can actually look at option prices, because options or derivatives, more precisely, the prices of derivatives are linked to the price dynamics of the underlying through some expectation formulas. Okay, so it's a little bit complicated because you have to think about measure changes and stuff like this, but let's just say that an option price is actually an expectation of some future payoff, which depends on the stock. So therefore, you can get information about the underlying dynamics of S from option data. And fortunately, in the case we're looking at, both of these sources of data actually agree in the conclusion that not only is there a memory effect, but actually the kernel behaves like a power law kernel, like a fractional kernel, with a Hurst index with an H, which is close to 0. So in particular, it's singular, right? You see it in the form. So just to give you some visual information, I mean, as I learned from Raoul today, most of our plots are boring, and I will show you many boring plots later on. But maybe there are some not so boring ones.
Not for me, but I'm talking about the general public, right?
I guess it's a fair point. So here are data from the S&P 500 index. So on the top row is the index itself, and on the bottom row is daily realized volatility. And even just looking at it, you see there's a difference in the scale behavior. There's a difference in the kind of roughness. And I will tell you, I mean, of course, now this is kind of not so clear, but this is scales like Brownian motion. So here you have the typical square root behavior. I mean, this is more like a geometric Brownian motion than a Brownian motion, but still. Whereas here you have a scaling behavior with an exponent which is, let's say, 0.1.
Volatility is inferred sometimes, not observed.
Yes, volatility, this is a very good point, and this is actually a source of a lot of kind of uncertainty about this kind of questions, because as Fabio notes, I mean, this here are data that you can observe precisely on the market. There is no uncertainty whatsoever, but these are estimates. And there's all kind of statistical issues with these kind of estimates. Nevertheless, you can play around, like there are publicly available databases where people use 25 different ways to estimate these numbers, and the plots for the purposes of today's talk will be equivalent. That's equivalent. So, but yeah. Right. So volatility is rough from the time series point of view. And then the option pricing, the derivative market point of view would lead to plots like this. I'm not going to explain in detail what you see here. For the expert, this is an implied volatility surface for the same thing. So these are implied volatilities of options. And the thing to look at is kind of the slope of this surface in the direction k, in the price direction, if you like, at 0. And you see kind of visually that this slope increases, becomes steeper and steeper as the time to maturity goes to 0. And in fact, if you actually compute the slope and you plot it on a graph, that's what you see. So the blue dots are difference quotients basically on this implied volatility surface, and the red line here, okay, let me think about it. I would have liked to say that the red line is just a power law curve interpolating, but the big link here tells me this is probably a Monte Carlo simulation based on a volatility model. But it doesn't really matter. The point is, or I'm telling you that if you just fitted a power law through here, you would also get a fit which is nearly as good as this. So basically, the message is that you have this kind of explosion of this Q. I mean, in the context of equity models, this slope is called this Q because it's somehow, if you think about it, the volatility is somehow related to the variance. So this is a derivative thereof. And you see this explosion of this Q, which also leads you to this kind of behavior. As a matter of fact, this would also give you, so basically the power law of the skew here gives you the power law of the curve, if you believe in this kind of modeling framework. Right. Here you get similarly small numbers, actually a bit smaller. So maybe 0.05 rather than 0.1. But the message is, okay, so you are really not just, so the message is twofold. You have this memory effect, you have these kernels, but also the kernels are singular. And as I said, there are a couple of unfortunate consequences this has, especially from a computational point of view. I basically mentioned the first one, so just to simulate this, if it is even possible in some of the cases, this is a hard challenge. It's going to be costly. You have low convergence rates, so standard schemes have a strong rate of convergence H, which if you think that H is say 0.1, this is, I mean, from a practical point of view, almost no convergence at all. Peak rates are better, fortunately, so basically you can add 1/2. And all these, for instance, pricing, PDEs, etc., they are basically out of the window, except, well, let's go like this. Go back. Except, of course, if you can somehow reinterpret this equation as a Markov process. And there is a kind of trivial way how you can do it. Namely, you can say, okay, I just add the history to the current state. If I do this, then at least on an intuitive level, every process is a Markov process. Now, of course, this is computational, not really useful, because you immediately are in infinite dimensions. But it turns out there's a very clever, very simple, very clever, better way of doing this, which is from a paper of Carmona and Coutin from 98. And I want to show it to you in the simplest case, namely in the case of a Gaussian-Volterra process of a kind of fractional Brownian motion.
Just a quick question about, are you considering kernels that are state dependent or just that are not?
No.
Okay. So this is not just an example, it's actually.
No, I mean, before it's an example because we allow state dependent dynamics modulated.
But Markovian state dependence, and then so the A.
Yeah, if you like, yes. But of course, yeah. But of course, due to the kernel, it's not Markov.
Yeah, of course.
So, okay. So again, let's do it for this Gaussian-Volterra case first. So the thing is, if you have a kernel which is completely monotone, for instance, the fractional kernel, then we can write the kernel as the Laplace transform of a measure. in fact, in the case of this kernel, this measure has a density, and the density is again a fractional function. And now we can simply apply stochastic Fubini. For the stochastic Volterra equation, I mean, it may not be very clear how to simulate at all. And if you do it, how to derive rates of convergence or stuff like this. Whereas if you simulate, whereas this is a standard SD, so you have all the theory available, the only thing you need to think about is, of course, what is the rate of convergence, or what is the how does the convergence of this Markovian approximation to the true process? Right. This looks very simple, but as I will show you, there are some catches here, especially in the singular case. So, but let's go through it. Let's say we are thinking about strong approximation. Well, first of all, if we just look at the diffusion part of our stochastic volatility equation, in order to apply Ito theory, we kind of need the kernel to be square integrable, right? This is kind of minimal assumption. Even if you take sigma to be a constant, you need the kernel to be square integrable. So it makes a lot of sense to work under this assumption. And as a matter of fact, a nice result by Aurélien Alfonso and Ahmed Kebaya shows that in fact you can bound the L2 error in the solution by the L2 error in the kernel, which is great news because now you have replaced a stochastic problem by a deterministic problem, right? You just need to understand if you want well, it's not even a quadrature error anymore, right? It's just, yeah, you have that kernel, you have a sum of exponential. What is this error? And as a matter of fact, in several cases of interest, this can be worked out explicitly. So the next question, of course, is now, I have not yet told you how to choose a quadrature. And this is where things start to become a bit more tricky. Because, well, what's the easiest quadrature formula that we can think of? Maybe it's something like a trapezoidal rule. And then it turns out for the fractional kernel, if you do this, you get an error that behaves like n to the minus h. And again, remember, h is very small. So we're in a very singular setting. So this is a very, very poor rate of convergence. Similarly, Philip Harms, in another very nice paper, he considered actually the Gaussian Volterra case, and he considered Gaussian quadratures. So basically, subdivide the positive line into some geometrically spaced intervals and do Gaussian quadrature on each of these intervals. And what he gets is similarly a rate that now depends. Okay, little n, lowercase n here is the number of intervals. Lowercase m is the order of the Gaussian quadrature on each interval. So in other words, the number of points is n times m. But you see, okay, you can increase the rate by playing with the order of the quadrature formula, but you still have this annoying h appearing. So in some sense, you have not really won that much. Now, in fact, if you go one step a little bit further than Philip Harms and now decide to choose these two crucial parameters, n and m, depending on each other, it turns out that you can actually get much better rates of convergence here. Because what we showed in our first paper was that, in fact, you get an error bound which is exponential in square root of the number of weights. And note that, okay, this is, of course, I was kind of blown away when I saw this, because I certainly did not expect something like this to be possible. But one thing that is still the case here is that as h goes to 0, this term blows up. So basically, you lose convergence when h goes to 0, and it has to be like this, because when h goes to 0, your kernel is no longer square integrable. Therefore, you know, this has to happen, right? But it's annoying because again, our H is very close to 0. So basically, right.
Ask a question.
Sure.
So at the beginning, you mentioned that H, capital H, is, I don't know, 0.1. So is this, when you say it's very small, do you have in mind something like 0.1 or something much smaller?
Already 0.1 is.
Because you take the square root of about 10, which is okay, I would say.
No, I agree. I mean,
But if it's 10 to the minus 3.
Yeah, so there are two effects. I mean, this is one effect. There's another effect which is actually linked, and this is the size of the larger speed of mean reversion, because that kind of controls the stiffness of the problem. And in a way, I mean, this result is really built on I try to minimize the L2 number. I don't care about properties of the resulting system. And if you do this, you will see very, very high speeds of mean reversion. Like this. And this is okay, let's put it like this. For some models, this is okay, because you can do splitting schemes where basically you take advantage of the fact that, of course, the mean reverting part of the dynamics you can solve explicitly. But for some other models, and we'll talk about this later in more detail if I have time. This is a real issue, right? But the good news is that, as a matter of fact, for popular models in the stochastic volatility class, we can reduce. Yes. We can reduce the number of nodes compared to the earlier works by a lot. So basically, we see that n around, let's say, 10 is enough, which of course means that speeds of mean reversions are, astronomical. But still, number of nodes is not so bad anymore. And you see, I mean, these are results of for h equals 0.1, the error in terms of number of nodes. So of course, you see, compared to the trapezoidal rule and the Gaussian quadrature, you just are in a different regime. But also, this also shows not just in this theoretical error estimates, but it also shows in the when you actually do option pricing. So maybe one example is this rough Heston model. We are going to talk about it more. And you see that basically, if you use a trapezoidal rule, you need about 1,000 nodes, and for our construction, 6. It's really a big difference. But again, this is the story about the strong approximation. What about weak approximation? Because for this kind of application, again, this is option pricing. Actually, we should care about the weak rather than the strong error. And there's some indication that in some cases, you actually don't need L2 for the weak error. So there's a very recent paper by Bossi, Martinez, and Bauer, where they get under also some special dynamics a weak error bound, which is not quite L1, because it's L1, but also L1 in k squared. But it goes in this direction. And for the rough Heston model, and I have written down the dynamics here, it actually turns out that the weak error can indeed be bounded by the L1 norm in the kernel. The reason here is you have this affine structure. And if you have heard of affine processes without the Volterra, you may know that these are processes where you can basically characterize the characteristic function of the solution. in terms of Riccati equation. And this means that somehow you don't actually need to go through Ito integration in order to construct a solution. And it turns out for the Volterra case, this basically works the same way, except that now your Riccati equation is a fractional Riccati equation. Formally, I mean, it even looks exactly the same way, except for that. And then it turns out, I mean, there are two results here, like Abijaba and Euch, they kind of proved for call options, but they had to use a modification of the actual Markovian approximation. And then we managed to actually prove a similar result, but paying a little price here in an additional exponent, which actually is for the honest Markovian approximation. But the bottom line is L1 is good enough. And why do we care? Well, it's not so interesting. We care because it turns out that if you only need to worry about the L1 error, you can somehow stay away from the tails. So basically, we get this result now in terms of the error of the L1 error. We get similar exponential in square root of n, but now you see the prefactor here does not explode as h goes to 0. In fact, it is finite for h greater than -1/2. And as a matter of fact, you can actually apply this for h greater than -1/2. So there is a way to make sense of the processes, even though, you know, fractional Brownian motion would not exist then, right? But still. And this also means that I don't know, I don't have these results here, but this also means that the speeds of mean reversions that you encounter can be reduced drastically. So basically, this is the prefactor. Of course, it goes to 0 for the L2 case, and it doesn't go to 0 for the L1 case. But maybe, okay, do I have this here? No. So basically, the bottom line of these boring plots is that reference to is that
I don't find it boring.
is that now we can, I'm looking for a specific one, but I don't see it now. Now we can basically reduce the speed of mean reversion, which was 10 to the 12 in the L2 case, to about 100. Right? And this actually makes a lot of the numerics feasible. And yeah, how much time do I have left?
10 minutes.
So I will jump through some of this. So basically, the bottom line is, compared to the earlier plots, you can again reduce the computational cost in terms of number of weights and nodes. But as I said, this is actually not the main point here. The main point here is that now we're in a shape where we can actually go to simulation. So for the previous L2 approximations, we tried, but we did not manage to translate these approximations, this Markovian approximation. Basically, we did not manage to solve these SDs, Markovian SDs. In some cases, as I said, some splitting tricks actually work, but in others, no chance. And the case where it doesn't work is, again, the rough Heston case, where you see, where basically you have an interplay between possibly very high speeds of mean reversion and a square root term, which becomes really deadly. Right, so this is a summary. So the system basically looks like this. We have, again, these n components, which basically look all the same in the second part of the drift and in the diffusion part. And the add a mean reversion part individual. And the first question that arose actually when trying to analyze this kind of model is, what's the state space? Because you see, if we look at, let me go back. If you look at the rough Heston model itself, I mean, as a matter of fact, weak existence and uniqueness is known, but strong uniqueness is actually not known for this model. So there are some considerable challenges left, but still, from the point of view of the state space, it seems pretty easy because V has to be non-negative. Solution is non-negative. I mean, actually, S and V, both of them have to be non-negative. And in fact, it turns out that this is the case. So basically, if we now go to the Markovian approximation, the first thing we observe is that our approximate V is this linear combination of the VIs. So the kind of natural assumption is that the VIs have to lie on this half plane such that their linear combination is non-negative. But in fact, so this would be this guy here. In fact, it turns out that more can be said. So in fact, it turns out that the actual state space is smaller than this, as a subset of this. And this took us quite some while to understand. I mean, there were abstract characterizations around, which actually suggest that D should be a cone. And it turns out that, well, you can write it down explicitly what the state space is. I'm not going, basically the state space is a cone, and there are some conditions on how it looks like, right? So we characterize it as a linear transformation or an affine transformation, more precisely, of Rn plus. I think this should be Rn plus, which is completely explicit. So basically, I don't want to go through the conditions because I don't think that they matter so much. But the image basically you should have in mind is the following. So basically, the half plane is this one. But in fact, the state space is considerably smaller. It's this kind of cone. This has, of course, consequences. First of all, for the analysis of the approximation, but also, for instance, if you were to think about now applying PDE methods, for instance, you really want to know, okay, what is my domain actually?
Zero volatility is accessible?
I don't know. Yes. I mean, numerically, absolutely. It loves to be at zero.
Is this plot showing negative volatility? No,
it's just, it shows. Yeah, okay. Excellent question. These individual VIs, they are allowed to become negative as long as the sum, the linear combination, is always non-negative. But yes, absolutely. I mean, these kind of effects where they seem to shoot over, this is a drawing artifact. This is not actually. Right. So as I said, the main challenge is the speed of mean reversion. Another challenge is that by construction, as we discussed with Raoul a few years ago, you may remember, by construction, all the scales here are equally important. So it's not like often in stiff problems you can identify the really important kind of submanifold, like subdynamics. No, by construction, all of them are equally important. And thanks to Abdulatif, actually zero, which is a huge problem because of the square root, is very often visited. Right. So if you failed attempt, drift implicit Euler did not work. Replacing the fast components by the invariant distributions did not work. Here is now what I was looking for before. So basically, the speeds of mean reversions are drastically reduced by going to L1 approximation schemes, if you like. So basically, to put some number for h equals to 0.1, from 10 to the 8 to 8.7, for h equals 0.01, from 10 to the 25 to 17.8. So basically, the bottom line is, if we are working with a kind of L1 optimized sets of point nodes and weights, we are in business, whereas in the L2 optimized case, probably can give up. And this is actually what happens. So basically what we use is we use a moment matching scheme from the literature, which turns out to work best for all the schemes that we do. And then we couple this IAM speeding up. We are coupling this with some kind of splitting scheme. Nothing very fancy here. So if you're interested in the details, please look at the paper, or we can share the slides afterwards. And then let's look at some numerical results. So basically, these are simulations of rough Heston, and I should say that this is more or less the first really converging simulation scheme for this model. And it looks very strange. First of all, this plot, the stock price, okay, in some places it looks like you would expect the geometric Brownian motion kind of process to look, but in others, like here, it doesn't really look like this. But of course, what happens is the V process really, really likes to be zero. So it spends a lot of time close to zero, and it is very rough. And that's, I think, the reason why you see this kind of strange curves. The stock price process, we have not actually done a proper numerical analysis of these schemes, but the empirical results indicate the weak rate of convergence of 2, which would be in line. I mean, the moment matching scheme should produce rate 2. Well, it was not developed for rough Heston, but for standard Heston, nevertheless. And I would say it performs better than the competitors. So basically, we compare against a fifth implicit Euler scheme and another moment matching scheme, the so-called HQ scheme. Weak here means our scheme that we presented, and you see it's much closer to the true. I mean, basically, I don't see a difference to the true smile in this case. By the way, true smile here means something computed by the Fourier, by the characteristic function. And yeah. So basically, two things that you see. First of all, you do see some kind of second order rate of convergence. So here we have n equals 3. So we have 2 relevant speeds of mean reversion. You also see that the rate of convergence is generally speaking achieved after, I mean, for time steps which are smaller than 1 over the highest speed of mean reversion, which is generally expected for this kind of problems. Yeah. And basically, you can also see from this picture, we get very small when you are now pricing a whole surface. Basically, it seems that n equals 3 dimension of the approximation is enough for practical applications. And that, thank you for your attention.